Okay, so hopefully you have tried filling in the blanks over here where should be sigma x y, y z etc. If not, let us see how it is. So, we said sigma I j, sigma in I direction in j on j plane. So, as you can see this is what, this is a z plane, and if we go in this direction it is also z direction. So, this becomes sigma z z. Now, this is z direction, but we are going in z plane and y direction. So, this will become sigma y z, this becomes sigma x z. Now, similarly, if we go over here, it is sigma x x, it is in the x plane and in the x direction. This is in the x plane going in the y direction. So, sigma y x, this is sigma z x. Similarly, over here if we come, this is sigma z y, this is first actually we should write sigma y y, and this is sigma x y. So, now you know what are the 9 components, what are its meaning. So, the x x, y y, z z as you can see are tensile and compressive type. The other ones with mixed indexes, they represent shear forces. So, you are doing some you are deforming it with a shear kind of force. So, these x y and y z with mixed indexes represent the shear. So, now once we understand this, something similar would also be representing the strain. So, now let us move on to understand what are the different strains in a system. And in any standard textbook and the one that I am following, which is the Hosford and Cadell, you would see that it can be represented. So, let us say we are first will be talking about 2 dimension, because the understanding can be easily extended to 3 dimension and it will be much easier to understand in the 2 dimensions. So, let us say to begin with you have element on the component, the 2D element, which is represented by A, B, C and D. Now, let us say that after deformation there is also some amount of translation, not only deformation, but also some amount of translation. So, it has, this is the new position and new shape. So, now you have A prime, B prime, C prime and D prime, and we will define that this is to begin with, this was at x, and to begin with this was at y. Let us say it is the size of this is a small element. So, the size is represented as delta x, the size over here is represented as delta y. Now, let us say that it has got displacement by u x. So, u represents the displacement part, the translation part. U x. So, this part has A has moved from here to here by u x. So, how much has D to whatever is parallel to this moved onto? First, our first hunch would be to say that this should also have moved by u x, but then you have to realize that there may also be, this is not only translation, but there is also translation and deformation. So, in as a general case, let us say that there is a elongation. You can, if it is getting condensed, we can assume it is negative elongation. So, as a general case, let us say it is elongation. So, there will be some elongation and therefore, this length can be represented so what we are actually, what we should be, let me, so we are talking about this D double prime. So, how much, where is the D double prime with respect to D? This is u x plus whatever deformation has taken place, and that will be del u x by del x. This is elongation per unit length, and what is the total length? It is into delta x. Similarly, if we say that this this is y and this part A to A prime has moved to u y, now what we are interested in finding where has B to actually B double prime moved. So, this is your B double prime. So, here also the first hunch would be that it has moved only uy, but you know that there is also some deformation, and the deformation per unit length is can be given by del uy del y, and the total length is delta y. So, this will become del uy by del y times delta y. Now, let us also represent for the shear part, let us say that this is equal to d and this part is equal to b. So, now we are in a position to describe or define the different strains. So, coming back to how would you define EXX or linear strain along x, it will be simply A prime d double prime minus AD by AD. Now, going over here you would realize what is A prime d double prime, this is this length plus this length. So, first let us write this part which is ux plus del ux by del x delta x, plus we need to add this particular part which is nothing but delta x minus ux. So, this is delta x minus ux, this part is whole A prime d double prime. Now, we have to subtract AD which is nothing but delta x and then divide it by delta x AD, and you would see that it will come down to nothing but del ux by del x. So, EXX is equal to del ux by del x, and once we know EXX we can similarly define EYY EZZ. Now, let us before we get to that part, let us look at how will the shear component look like, and we want to stay with the drawing. So, I will delete this part. So, first we will get the shear strain and then the uniform strain. So, gamma xy is nothing but we are talking about xy. So, b by delta y which is over particular length. So, this is the transformation or the, so this is the deformation b in the x direction along on the y plane which is the AB. So, with this will be defined as b by delta y, and therefore, what you would see is that this will come to del ux by del y. So, we have not described b, but this is what b will come out to be into delta y, and we have to divide it by delta y. So, gamma xy is equal to nothing but del ux by del y, and similarly you would see that gamma yx would turn out to be nothing but del uy by del x, and therefore, Exy which is defined as 1 by 2 gamma xy plus gamma yx would become 1 by 2 del ux by del y plus del uy by del x. So, now we have shown the derivation for a linear elongation xx which can be extended to yy and zz. We do not have a zz, but if it had a 3-dimensional component it can be extended to that, and the shear deformation and the uniform shear deformation Exy. And therefore, let me write it all together at one place. So, we can come back to it when needed. Exx is equal to del ux by del x, Eyy is equal to del uy by del y, and Ezz is equal to del uz by del z. Exy is equal to Eyx, because now in this format Exy would be equal to Eyx, and this would be nothing but sum of the shear deformation by average of the shear deformations. Similarly, Eyz is equal to Ezy is equal to 1 by 2 del uy by del z plus del uz by del y, and Ezx which will be equal to Exz would be equal to 1 by 2 del u z by del y plus del u y by del z. So, when we write in this format, we know that E x y will be equal to E y x in the matrix, E y z will be equal to E z x in the strain matrix, and so on. And when you define it in this format, you would also realize that we have automatically taken or gotten rid of the translation component. It will not show as a strain. So, if you say that your delta L has moved from over here to here, or a particular length has moved from here to here, then there is no strain. If you go by this definition, you would see that has already been excluded. If you have the strains like this, then you can also get the hydrostatic deformation. P equal to minus 1 by 3 E x x plus E y y plus E z z. Now, using this is again fundamentals of solid mechanics. If you are given G equal to shear modulus lambda is equal to Lames constant, we are not deriving these, we are just going through briefly so that we can then apply all these for our purpose. So, let us say these are given, then from Hooke's law for isotropic materials, we can write the following. Now, we can write the stress terms. So, sigma I j is equal to 2 g E I j plus lambda k k delta I j, where delta I j is the delta function. When I is equal to j, it is 1, when I is not equal to j, it is equal to 0. Therefore, sigma x x is equal to 2 g E x x, and as you can see that over here x x is same I equal to j, therefore, you will continue, and therefore, we will have lambda, okay, and here there was a term E k k. So, we will have the term lambda E x x plus E y y plus E z z. Similarly, you will have lambda y y equal to 2 g E y plus lambda E x x. In all these, you can see that I is equal to j, therefore, delta I j is equal to 1, and therefore, we are getting these components. And very soon we will see in one particular case, not one, but the where this is not equal, I is not equal to j, that all those components will disappear. Now, we will come to the shear stresses. So, what we have looked at over here are the normal stresses x x, y y, z z. Now, when we get to shear stresses x is equal x and y. So, you can see x and y are I is not equal to j, and therefore, delta will be equal to 0, and therefore, what you will end up with is 2 g E x y. Sigma y z is equal to 2 g E y z. Sigma z x is equal to 2 g E z x. Where the other components, these are all other components are 0. So, now we have looked at the fundamental equations that will be required to obtain stress and strain relations. We know that we have the stress and strain relation assuming linear elasticity model and continuum mechanics. So, with that, we are now in a position to look at one particular example, and what we will start with a screw dislocation. So, we know the basic relations. We know the basic relations stress strain, and we will apply it to find what will how the form of the strain for screw dislocation should look like. So, let us first draw what a screw dislocation would look like. So, using the Volta model, we have a hollow cylinder and there is a cut. The cut is on the left side and there is a displacement. This displacement is along the z direction. So, one side has been displaced with respect to the other in the z direction, which is what you see over here. And if I draw it to show the hidden edges, this is how it would look like. So, this edge ends over here and there is this displacement. Now, if you remember from our understanding of the screw dislocation, no matter how far you go, the displacement between the two sides would remain constant, and what is that constant distance? That is equal to b. If you remember, this will, so this does not have anything to do with what is the radius you are taking. You can take whatever radius you want, but this displacement, and we are assuming that we are far away from the core. So, if we are let us say this is the dislocation line, since we are talking about a screw dislocation. So, this is the line vector and also the core of the dislocation, and no matter how far you are, you will have a displacement equal to b. And let us say this radius that we are talking about is r, and since this is a hollow cylinder, let us assume that this thickness is very, very small. So, now next what we need to do here is we will spread this, assuming that this is a cut cylinder and it is a very thin cylinder, we are in a position something like a paper. So, you can assume it is a paper and we will open it. So, how would it look like? So, what is this displacement? Like we said earlier, what this displacement is equal to Berger vector b. At different points within this, you can see it is less than b, but the final or the maximum displacement is equal to b, and this whole length will be equal to 2 pi r, and as we said that the distance r has not much to play over here, at least now, because no matter what distance you are, that this will be the form of the open cylinder. After you open it, this is how it would look like. So, this would also be equal to b. And now let us say that we have some axis and we will align the axis along one of the cut. So, let us say the x is oriented or is aligned with the direction where there was a cut. So, this is x and this is y. So, now let us say I am talking about some particular plane on this cylinder which is at an angle theta. So, this is our x, this is our y, and I am going some angle theta with respect to x. So, if we talk about that theta, then in terms of length, this will be equal to theta r, assuming theta is given in radians. So, this distance is theta r, meaning we are talking about this distance in here. Now, let us try to define what will be the ux, uy and uz over here, then we will be in a position to describe the strains. So, what is u x over here? What is u y over here? So, x is in this direction, y is in this direction. Has any displacement taken along x direction? No. So, u x is equal to 0. Has any displacement taken along y direction? No. So, u y is equal to 0. But has any displacement taken along z? And the answer is emphatic yes. And what is that displacement equal to? This is equal to theta r. If you are talking about certain plane which is at theta orientation, then it is theta r by 2 pi r, and if the total is b, then it is the ratio of these two, and this is equal to b theta by 2 pi is equal to b by 2 pi. In terms of, if we want it in x and y coordinates, then it will remain b tan inverse y by x. Now, first thing you have to realize that we are talking about the strain, not strain, but the total displacement in z direction, and what we get that it is u z is not a function of z, it is a function of x and y. So, that is something very interesting, but not really of concern right now. So, this is the form of u z. Now, with that understanding of u z, you can go back and see what will be E x x, E y y. You would see that E x x, E y y, E z z, E x y and E y x. Let us see the equation a little bit. So, we have the E x x, E y y, E z z. What do you see? It is talking in terms of u x, u y, and this is talking in terms of del u z, but with respect to del z, but we know that there is no z component. So, all these will turn out to be 0. Now, similarly, when we go to x y, then we have del u x by del y, we have plus del u y by del x, and E y z. E y z is the only component where we would see that there is a non-zero component, and therefore, all other elements over here, which is E x x, E y y, E z z, E x y and E y x, they turn out to be 0. The only non-zero components are E x z equal to E z x, which is equal to 1 by 2 del u z by del x. In the E x y and E y x, you need del u x, del u y, and all those are 0. So, those are also 0. These 3 already we have seen equal to 0. So, this is the form of the equation del u z by del x. The other one del u x by del z is again 0. So, what we get is we are differentiating using the chain rule. So, we have first differentiated assuming y by x as one component, and then we differentiate y by x with respect to x, and we get y by minus x square, and therefore, this will so there is a minus term which comes out over here. This is becomes 4 pi, and this becomes y by x square plus y square. This x square will get cancelled, or if you want to write it in terms of theta, then this becomes minus p by 4 pi sin theta by r. So, this is the E x z component. Similarly, you will have the E y z component, which will be equal to E z y. So, here also we have only del u z available, the z del u x is 0. So, this is del u z with respect to del y, and therefore, into 1 by x, which turns out to be b by 4 phi x by x square plus y square, or in terms of theta it will be equal to b by 4 pi. So, there is a kind of symmetry between the two strain values that we have obtained. So, these are the xz and the yz relations. Now, what do we see? What are the important things that we can deduce from here? One that you will see is that both Exz and Eyz, meaning the strain, the shear strain xz and the shear strain yz, they are proportional to 1 over r. What is the meaning of this proportionality with respect to 1 over r? What it means is that at very large distances, at r tending to infinity, your Exz or Eyz will tend to 0. Now, this is something characteristics that we defined is associated with dislocation, not with disclination, which is the other kind of defect. So, this we can see that even mathematically we obtain something like that, like this, that at r tending to infinity we get Exz and Eyz tending to 0. So, this is and in fact, it is very important information, because what it tells is that this is the short range strain. It is not that there is one dislocation line over here and you go miles and miles and you still see very large strains, or the strain keeps constant or it keeps increasing, because if the strain is even constant, what it would mean is that your energy, stored energy, would keep increasing. Now, next question is that we have strains, how would the stresses look like? So, for that we will use the Hooke's relation, and in the Hooke's relation again, let us see how the Hooke's relation was. So, what you want over here is that you have for sigma xx there should be Exx, for sigma yy there should be Eyy, for sigma zz there should be Ezz. So, all of these are not present, what we have is only Exy. So, therefore, what we will not Exy, sorry, Eyz and Ezx. So, what we will be able to get as a stress is only sigma yz and sigma zx. So, just like in the strain, the only two components that are non-zero are sigma xz and sigma yz. So, what we get is that sigma xx is equal to sigma yy is all, these are all 0. Sigma xz, which is equal to sigma zx, using the Hooke's law we can write it like this, minus Gb by 2 pi into y by, and again if you want to write it in theta, similarly sigma yz is equal to sigma zy is equal to Gb by 2 pi or we can write it as Gb by 2 pi cos theta by r. So, we have the relation for stresses, and as you see that we have only 2 components, or in fact 4 components if we look in the matrix form. So, we will look at the matrix form in the next class. In the meantime, you try to guess what are the elements in this 9 components which are non-zero and where do they lie. Similarly, you draw the matrix for the strain component. So, this is sigma tensor, this is strain tensor. So, go back and try to write down, fill in this box, and we will meet you in the next class. Thanks.